Hello, everyone. We are going to do a special re-recording of the webinar that you are seeing today. On the day of the live recording, we did have some technical difficulties. So Sergey and myself are going to, we are re-recording this webinar for you all and to enjoy. So we're going to have some of the Q&A questions that we answered live on the day. We are going to repeat that. So if you stick around to the end, you will see those questions. And then any other questions that we did not get to during the webinar, you will be receiving a link with a written answer and response to all those questions that we couldn't get to. So without further ado, I'm going to introduce Sergey to you all, and he's going to do a presentation on nebulizers. And then I'll do a brief presentation on some interference-free standards, and we'll go ahead and get started. So if you're not familiar with Sergey, Dr. Sergey Lincoln is the co-founder and managing director of TSP, that's Texas Scientific Products, a supplier of high-quality consumables and innovative sample introduction systems for ICP, atomic emission, and mass spectrometers. Prior to starting at TSP, he worked as an applications laboratory manager for premier instrument manufacturers of both the ICP OES, ICP mass spec, and microwave digestion equipment. An analytical chemist with extensive scientific background, Sergey utilizes his 36 years of experience in atomic spectroscopy to help solve everyday real-world material analysis problems. And that is definitely true. I can attest to that firsthand. At TSP, Dr. Lincoln directs the new product and business development while keeping the focus on what he likes the most, problem solving. Sergey received a master's degree in optical electronic systems and a PhD in analytical chemistry. So Sergey, thank you so much for joining us again for the webinar, and I'm going to turn it over to you.
Okay, all right. Well, thank you. Thank you for such a warm introduction, and let's dive into the in the world of nebulizers. All right, so I'm going to get straight to the world of nebulizers without introduction to our company, so just to save valuable time. So most of the people knows us, and if you don't, you can look at our website. But we do manufacture the nebulizers, and we supply the other nebulizers, all the consumables. So why did we choose this particular topic and decided to talk about the nebulizers? Why it's so critical? So when you're buying in the process of getting the spectrometer, right? And if you get it already, so it's a pretty significant price tag. It's going up to $250,000. And if little accessory that comes into it is around a few hundred to a couple of $1,000 is just not right for whatever reason for your application, then all of these good-looking instruments is just turns to a set of good-looking panels and a bunch of electronic boards. If you look at what is the nebulizer is, and it's a pretty simple thing, right? That the Wikipedia express it as the device or apparatus that converts liquid into the fine mist. And we deal with nebulizers in our everyday life, right? With the paint spray, or for medical purposes, there are inhalers. So that's the devices that produce liquid into the mist. But when it comes to analytical nebulizers for ICP or ICP-MS, the choice is overwhelming, actually overwhelming for everyone, including the industry professionals. And in order to get to this, this is what we do. We help. And if our customers are reaching out to us, or you guys reaching out to us with problems, or with, that's what we do. We're trying to help and navigate and resolve the issues that you're currently having. When we ask, what type of nebulizer do you have? 9 times out of 10, this is what we hear. It just came with my instrument. And what it means is the ICP manufacturers, they have what's so-called default nebulizer. And it's not necessarily best from the technical standpoint, because there are some other considerations there, the price, availability, being protocoled with the QC, QA things. And this is the default thing. So it also depends on the sales professional that you dealt with. If you dig into what you do, so then you may end up with a right nebulizer. If not, so you may be struggling. And if that would be so simple, And sometimes it works, right? But if you're running into the something like that, which is what I call real world application, it could be clinical samples with direct blood, the bunker oils, the industrial samples with particulate, or with oils for refining purposes. That it's a waste oil from the food chain. So the default nebulizer will be unlikely the one that is successfully to be used. The ICP manufacturers do provide some help, and you can find it on some of the website. This is just one example of so-called nebulizer selection guides. And so here is just one example. You see a number of nebulizers. There are different parameters there, the efficiency, the precision, HF tolerance, and ability to run organics, and also like self-aspiration. I don't see here the particulate tolerance, but that comes on. This is the first page. So this is a bit of a help, but it could include few pages, and it really requires some help from the outside. Now, if we look at all of that, and let's see what would be the ideal or the dream nebulizer. Well, it's no nebulizer at all, meaning you can set it and forget it. So this is not my line. This is actually the one of the famous commercial lines that have been used in the different industry. But I felt that this is what actually would be properly describe what we would ideally want from our nebulizer. Just set it and don't touch it. That would be the ideal world. In what it means, it will run reliably, it provide consistent performance and stability, and we don't have to touch it, so it will be no maintenance or minimum maintenance with it. If we transfer it to a more technical language, or translate it to more technical language, so then we expect from our nebulizer provide us best efficiency or sensitivity and precision. It should handle samples with high amount of total dissolved solids. Also, it should be able to handle the particulate content, because the general recommendation is to filter the samples and prevent nebulizer to be clogged and all of that, which sometimes is not even feasible to do for some sample types. So we would like the nebulizer to be able to handle it and to be HF resistant. So this is not all of labs obviously want to deal with HF, but some of them do. So it's just it gives a bit of a universal use for the nebulizer. So it's also HF resistant, so you don't have to switch between a few of them. So that's what our dream is. Now, if we take a look, and this is just some of the selection of the typical nebulizers that are being offered on the marketplace, and try to go and filter them from this perspective that I mentioned of the criteria, of the 4 criteria in terms of the performance. So let's see how it works. All of these nebulizers that you see here are hollow solids capable, at least per we're going by the manufacturer recommendation. You can see here different what's called V-groove types, which I'll describe a bit later. So there is enhanced parallel path, concentric nebulizers, flow blurring, cross flow, and some of ours what we call thin film induction nebulizers. So all of these are high solids capable. Now, 2 concentric nebulizers, not all of them are high solids capable, but these particular 2, they do have some design features with recessed capillary that I will show a bit later in detail. So they do handle high amount of salts. So then we go to our next criteria, particulate content, and the concentric nebulizers, so they're great for the efficiency, precision, but when it comes to particulate, so they having a problem with it, right? So then there is a different type nebulizer that was brought up to replace the concentric called flow boring. So that has a higher particulate content, but still it's limited to 150 microns. And this is what we have left. Now, when we go to the next requirement, which is best possible precision and sensitivity, so you can see that the V-groove type nebulizer, and this is again displayed on one of the ICP manufacturers' websites, stating that, yeah, the V-groove type nebulizer, in this case, they do provide high amount tolerance to high TDS in particular, but will struggle with precision and sensitivity. So this is the challenge for the nebulizers that non-concentric, what we call. So then if we look at, so that's what we have left after filtering the other two criteria. And then from these nebulizers, what will offer the best possible precision and sensitivity? So the V-groove nebulizers, as we saw on the previous slide, they struggle with that. So then there is one more V-groove nebulizer left here. And if we apply HF resistant criteria, so obviously glass will not be able to do that. And then what we have left with. So this is just, filtering and getting the nebulizer to the marketplace and then going through all of these criteria. So let's look into the design of, just dig into the design of different nebulizers and why they perform the way they perform. So nebulizers look alike. And if you look at these two pictures, so these look pretty much the same or very close. And even industry professionals do not recognize the difference between them. But the difference is fundamental. So one nebulizer is what we call concentric type, and then I'll explain what it means. And this one is non-concentric. So in the main difference between them in terms of the design is the internal diameter of the sample channel. And you see here, the concentric nebulizers have very small diameter, while the non-concentric nebulizers, there are a few types of them, so they much larger. And that what helps them to handle particulate content and high TDS as well. So here is the design concept of concentric nebulizer. Quite often in the industry, it is referred to as a Meinhardt type, and you can see here on the picture that there is a Meinhardt and trademark. So the reason for that is these nebulizers this nebulizer was developed, or configuration of it, by Dr. Meinhardt in the middle 70s, I think 73 or 74. And that's been great and that's been improved over the years, but the basic design is still the same. It is what we call tube within the tube. So you'll see the sample capillary, that's tube, and it's represented with the circle here, is inserted into the outer shell of the outer body of the nebulizer. And this is the largest circle here, and between them, there is a distance, and this is where the gas is coming from. So the key here is very tiny. So it looks pretty big on the picture, but in real life, it's pretty small. This is approximate range of the dimension. And the manufacturers of the concentric nebulizer don't disclose it on their literature for whatever reason, but in different publications, so people measure it, and this is where this number coming from. So if we try to compare how it looks in the real life, so 0.15 millimeters, 150 microns, and the thickness of the human hair average is 100 microns. If you Google it, that will show. So it's about slightly larger than the thickness of the human hair. That's how tiny it is. That's why the nebulizer has good efficiency and precision, because the gas is forced through the tiny opening creates a efficient high velocity gas jet that hits the liquid and that produces a good quality mist. But since it's small, so the particulate tolerance is limited. And here's what happens in the real life. So everything works well for clean samples, but so when you start to run something, there is a buildup, could be inside the sample capillary, it could build up inside the gas channel, and the indication of it is the pressure on your nebulizer, what we call back pressure, goes up. And that's also the monitoring tool. So some of the manufacturer's software even monitor the back pressure. And that's something you can look if you need to check the performance. Look at the pressure on your nebulizer. If it's elevated, it's blocked. If it's below the specified value, you have a leak in the sample introduction system. So that's a little bit of a jumping ahead to, troubleshooting of these performances of the nebulizers. So there is also a sample material that can be inside. And here is the picture from the live nebulizer taken from this publication. So the nebulizer design, so see the capillary, the sample capillary, sample channel is recessed, means it moved away a little bit from the orifice of the nebulizer. And that what makes it high solids capable or high salts capable. But still, the material can be built up inside. So it recessed so that the liquid can sort of rewash the area here, so the salt is not going to be building up. Because the other type of concentric nebulizers, they have the capillary that is flushed with the orifice, and they are not high solids capable. If you look at this picture that I've taken years ago that tried to explain people, what is the geometry of the concentric nebulizer. So this is a gigantic traffic jam from 50 lanes here, and it narrows down to 20, and that's why it's building up all of these things. So it's a restriction, but yeah, that's going from 50 to 20, and that probably reminds us what the geometry of concentric nebulizer is. So similar thing, it goes and restricts the flow of the gas here. Another type of nebulizer that's been developed by a company in Spain, Ingeniatrix, and the research group there, it's pretty clever, and it's been marketed exclusively by Agilent in the name of the OneNeb. So that's been developed to replace a concentric nebulizer. It has a decent totals of solids tolerance, and also can handle larger particle size according to manufacturer specs, but still limited to about 150 microns. The geometry and design of this nebulizer is quite different, and it's similar to concentric in some way, but the sample path is straight, it's not restricted, it's not changed over the length of the nebulizer as compared to some concentrics, and the gas is not coming like on the concentric under the angle. It's coming almost perpendicular, sort of like in a crossflow, but in a much contained space. And what it does, it mixes with liquid and creates the turbulent mixing, and that provides the efficiency and high quality of the aerosol, which is small particles, and make this nebulizer very efficient at this small sample uptake rate. But still, if you can look at this, the space here is pretty tiny, and you can get, that's why the particulate content is higher than on the claim to be higher than the concentric nebulizer, but still limited. To kind of get maybe sort of an idea of what a real high TDS tolerance and between all these nebulizers. So there is a work that's been done by Gary Mayer and been presented in the ICP Winter Conference in 2017. So he get all of these different nebulizers, which is Optimistic Cell is one of our thin film induction nebulizers. It's Mirror-Mist Enhanced Parallel Path. It's concentric nebulizer from one of the manufacturers of this, and the one neb, the flow blurring that I showed you on the slide before. So this is pretty exotic, I would say, matrix, but it just to give general idea on how these nebulizers perform. So when it started, and you can see here the bar represents the efficiency. So the concentric being the highest here, a little bit with in par with one neb, but these two nebulizers, Enhanced Parallel Path and ours, are pretty much in the same ballpark, maybe 20% less. And then when it goes through the run, you can see here that after about 1 hour, so the efficiency becomes the same because the efficiency of the concentric and one neb drops, and then here it becomes less, and then it drops here, and then it's almost down to nothing. Why the Enhanced Parallel Path and our nebulizer, thin film induction nebulizer, stay almost unchanged. So that's a exotic application, but kind of give you an idea what to expect in terms of the tolerance to high TDS when it comes to that. So we talk a lot about concentric nebulizers and their limitation, but what they are good for and what I think it would be best to use them at. So one of the very good use of them would be in case you have to run chemicals or reagents that are so aggressive they're going to eat through the or destroy or disintegrate any material available for the peristaltic pump tubing. So then you can use the concentric nebulizer to self-aspirate. Then you can bypass the peristaltic pump and get your sample through just the Teflon capillary connection that's used on all the nebulizers. Also, it's some of the clean waters, drinking waters typically, but some of the drinking waters that we saw here, yeah, I couldn't believe it. They look almost like industrial waters, so they were pretty tough. But for clean drinking waters, yeah, absolutely, the concentric nebulizer will work well. The other good application would be if you need to run high volatile organics and you don't have access to the expensive, good but expensive cooled spray chamber, then you can use the concentric, what's called micro nebulizer, with limited or small sample uptake rate, somewhere between 0.1 to 0.4 mils per minute, or even smaller if needed. And so that will get you a limited amount of sample to the plasma. It will reduce plasma load, and you will be able to run high volatile organics with high power settings and adjust that, but the plasma should be able to handle it by reducing the solvent load. So now we describe in details the concentric nebulizer designs, how the nebulizers that handle the particles and why they handle the particles look like. And here is the example of what's so-called V-groove type nebulizer. So this is the gem cone that manufactured and offered by Perkin Elmer as an example. You see here, it's a pretty large sample channel, probably about 0.7 millimeters, something like that. So then here, there is a groove. And then it comes to the gas comes from here, which is the sapphire cone that is being glued by epoxy into the big body of the nebulizer. So the sample comes here, and the V groove is designed to direct the liquid flow to the gas orifice. So it's a gravity-driven nebulizer, so that's why there is a V groove there, so that will drive or help to direct liquid straight to the gas. It's pretty solid nebulizer. There is some limitations there, but it works for particles pretty well. The other example is what we manufacture is similar concept with gas and sample being separated. And but there is no V groove. We don't employ the V groove on the tip of the nebulizer. It's a different action going on. That's why it's called thin film, that we work the surface tension to work, and that actually will work even without gravity driven. And it's pretty. The efficiency of this nebulizer is better, and it's better precision as well. Here is the anatomy of it, or the closer look at the tip, and you see here the sample channel is pretty big. It's 1 millimeter. That's why we called it virtual uncloggable, because unless you have, you get the saturated solution, just leave it there. So otherwise you simply cannot block the sample channel on this nebulizer. And here is why. Also, that simple diagram explains what's going on there. So you have the sample that's coming from, let's say, from the auto sampler, from your sample vial. And modern sample probes on most of the auto samplers are somewhere around 0.8 millimeter ID. So it's pretty big. And then it goes to the sample adapter that's connected to it. That's a typical range of the internal diameters, because there are smaller ones, but we don't use them because they're going to really be filtering this stuff, and you're going to be just stopping and removing this all the time. So it goes from the smaller size to, when it gets to the nebulizer, it's a larger one. So it's not like on the concentric, contrary to concentric, when it goes from larger sample ID to a smaller one, when it's restricted. That's why particle getting stuck there. Here, the particle, if it goes through that, which is pretty big, it goes to 1 millimeter and just comes out without any problems. So what would be the good application for nebulizers handle high particulates and things like that? So I brought this slide because we keep seeing that even for that type of application, it's agricultural soils where high production, so people have to get, processing 1,000 samples a day very quickly, and take the soil, and this is the part that, handling the soils, and then put them in the, along with extractant, which is going to be malic-3 or some other type of extractants. And then even they apply the filtering. You see here, the sample is still pretty, looking pretty rough. And we still hear from our customers that they're struggling with concentric nebulizer being supplied for this application. And here's clearly you can use any of non-concentric nebulizers for that when you see particles, and it will be just fine. The other good or proper use of non-concentric nebulizer is any analysis of oils, wear metals and oil. This is the bunker oil. This is really, really rough. And here is the waste oil from the food chain used for refining and getting, building some biodiesel and things like that. So you see here, the picture is they're sitting horizontally on the bench, and the oil is so thick that it's solidified at room temperature. So anything like that with oil, edible oils, vegetable oils, the wear metals in oils, used oil, so that all can be handled very well, or should be handled with non-concentric nebulizers. Now, here is the example of also of some of the performances. So when I mentioned that the concentric nebulizer is usually more efficient and provide better detection limits than non-concentric, but here is the example where it actually works the other way. So this is a publication where a group in Spain look at phosphorus in all kinds of petroleum product with high particulate content, and that include different type of oils and things like that. And they tested different or evaluated different type of nebulizer. They reached out to us because they were having problem with their current concentric nebulizers plugging all the time, and they used 2 of our nebulizers. So the surprising result here is the detection limit you would expect for concentric nebulizer to provide better detection limit, but in phosphorus, for phosphorus in this particular matrix, it worked the other way around. And you can see here the detection limit is actually twice better for non-concentric nebulizers versus concentric. And here is the just part of the conclusion of the paper that clearly states that. And the reason for that, if we look at the spectral background, so the phosphorus line in that used in the this publication to get, or this work to get the low detection limit was in the low UV spectrum range, where there's a pretty structural background. And actually, anyway, in organic, it will be structural background. So efficiency of the slightly high efficiency of the concentric nebulizer actually played here opposite way, and that's why the detection limit for non-concentric worked better. Plus, there was no clogging issues, obviously, with any of our non-concentric nebulizers. So now we talked about the detection limits, the good detection efficiency of concentric nebulizers. Here is the example where some of non-concentric nebulizers was successfully used to boost the detection, even the detection limits. And this work was done as a collaboration with Inorganic Ventures and CM. So we published it in the spectroscopy October issue. And there are two examples there for getting actually detection limits that's comparable with one that's done by ICP-MS. And that's for running cannabis, and as an example, because it has very strict requirements of detection limits, and also another example of running high purity copper. So this is the nebulizer that used there in this work is what we call Optimus Vortex. It's a non-concentric nebulizer with impact plate, and on average, it doubles the sensitivity as compared to any existing concentric nebulizers. So here is the design or geometry of it. It's, you see the sample and gas are separated like on other nebulizers, but, and you see here, it's almost look like our Optimist XL, right? So there is a sample, it's just impact plate was taken out from it. So you can see here, so that's pretty similar. But here is the impact plate. And what happened here, the initially created aerosol would get hit against the impact plate, and the aerosol particles would get dispersed to a finer mist. And that's why this was called improved gas-liquid interaction. It gives more energy, and then you get a finer aerosol, and the efficiency of this goes up. So when I explain this concept, I came up with the analogy of like a waterfall, right? So when water falls from the high elevation, high distance, and it hits the bottom, so this is the naturally created mist, right? Or a nebulizer. It's pretty efficient. So the impact action is here in action. And this is what happened, similar thing happening with this nebulizer, where, and you can see here the comparison between when the spray chamber is not misting and how dense the mist is. So we could probably put the picture of, you know, when you get the concentric nebulizer and compare the mist, but you see here, it's almost like a fog inside that, and that indirectly shows up the efficiency of this nebulizer. So when it comes to ICP-MS, the choice is a bit more narrow, because the modern ICP-MSs are designed to for smaller sample uptake rate. So that's why there are micro nebulizers that to be used, and so they're typically made or offered from HF-resistant materials, or clean. I should say cleanliness here is more important than the HF resistance. So it's PFA. There are some nebulizers made from Teflon, and there is a glass or quartz microflow nebulizers. So the alternative to it that we offer, again, it's non-concentric, what we call optimist ion. And the difference here is much larger sample channel. So if you look at this diagram, so all of the microconcentric nebulizers that use for ICP-MS have very small or tiny sample channel ID, because to make it work well at a smaller sample uptake rate. So it has to be small in order to handle it, produce the good mist. But we were able, with unique design, we were able to stand up and keep the sample channel ID at a pretty large size, so it can handle particulate as well. So here is the example of how this worked in real life. This is the poster that's been presented by University of Arizona, a lab for emerging contamination. Mary Kay, Mrs. Mary Kay Amistadi from university. So this is her poster, and you can see here some of the highlights. So this lab have to handle different type of samples from different researchers within the university. So today it could be insects, unique insects. Tomorrow it can be clinical samples, blood, and soil digest or wood digest, you name it. And the lab really, under this environment, when it go and change, it doesn't have time to filter it or centrifuge it that's normally required for any ICP-MS application. And they were struggling with what they have to deal with. But when we put, our nebulizer, we're able to go with, and this is just the snapshot of what they do within about 9 months, 17,000 samples with no blockages, and surprisingly, not even no maintenance. What we say about the filtering and centrifuging that would normally every lab have to go through, and that's what actually recommended by the industry manufacturers. So this is the best way. What is the best way to deal with nebulizer problems? Is prevention, and by prevention it means filtering the sample, centrifuging, pre-filtering, cleaning, maintaining, to do all of that. And that's obviously works, and that's what labs deal with, but that adds a cost and it's time consuming. So the cost is rising. So the average cost of this filter is about $1 per sample, and you can do the calculation. So if you can bypass that, you will increase your productivity, and it will help you to get cost of your lab down. So at the end, I would like to share with you our new products that we're pretty excited about. So it's it came up with the HF-resistant version of our Optimist XL glass or quartz nebulizer, and we called it Optimist Ultimate. It builds from being manufactured from the one of the high performance plastics called Ultim, and this is the peak version of it. It has similar design to what we have covered in the same patent, but what we see from the field is actually a increase or improvement in the performance, both on sensitivity and precision. And also the feedback that we're getting is, some of our users, they put it in, I think it's been on the market since the last PeatCon, which is a year and a half. So for a year and a half, they put it in and they did not even touch it, for some applications. Here is the example of the performance of this type of nebulizer. You see, this has been shared by the pure lithium, and there are different and difficult type of matrices for lithium battery industry. And precision, this is just demonstrates or shows the type of precision that you can get from this type of nebulizer. So this is pretty exciting for us, and we hope to get it to the market within next short period of time. And so I think I ran out of my time, and I appreciate your attention. And then I pass it to Mike.
Awesome. Well, thank you, Sergey. So I'm going to go ahead and share my screen for the second presentation of this webinar. All right. So for my presentation, I want to talk to you all about method development and more specifically the role of optimizing your standards to avoid some interferences. So why do you normally care about interferences while you're doing method development? And the main reason for that is because when it comes time to do method validation, you're going to run into problems if you have not accounted for the interferences that are present. So during validation, usually you'll have 7 key characteristics that you're worried about. Interferences are going to directly impact specificity. So that's making sure that you can get the same result on multiple masses on mass spec or multiple emission lines on ICP OES. And accuracy is going to be a big one. If you're running, a method validation and you have some control samples, if you haven't taken into account the interferences correctly, your accuracy is not going to be very good on lines or masses that have those interferences. So worrying about your interferences is crucial during method development, just so you save yourself some time in the end during method validation. We've spoken about this in the past. Thomas and myself did a webinar a couple years ago that has proven to be one of our more popular webinars about a custom method that we developed for ICP OES that measures 69 elements in one single method. So Thomas did the vast majority of the work on this, developing the method, and he focused a lot of his time on developing the standards to avoid interferences within the standards themselves, because some of the samples may not have the same interferences that our standard set was because we were looking at 69 elements. So that work was really critical, and I think it's a really good example of how worrying about your standard design can have a huge impact on your final method, not in so much of the accuracy and precision, but in this particular case, just a huge time savings as well. So definitely, if you're interested, check out this webinar. It's available on our website. If you go to our educational resources, our technical videos, you'll scroll down the page and you'll see it. This is what the thumbnail of the video looks like on this screen or on the slide. But check it out. We went into vast detail about the method development and the method validation for that custom method. So for today, I thought we would do a similar example, but change it up a little bit. So instead of ICP OES, we would talk about ICP mass spec. All right, so let's take a little bit of an in-depth look at EPA method 200.8. So if you're not familiar with EPA method 200.8, it's for trace elements in waters and wastewaters by ICP mass spec. The elements in blue here on the periodic table are the trace elements that you're interested in. The method also lists good internal standard elements. So those are the ones that I've highlighted in purple. And it's great because they cover the wide range, the full mass spectrum, which is great because your trace elements are going to cover that full mass spectrum. So you need that. What's not singled out and noted a ton in that method is some of the common major elements that are going to be present in your samples. So again, you're looking at waters, so expect to see relatively high concentrations of things like sodium and calcium and iron compared to what should be trace concentrations of things like, cadmium, cobalt, mercury. Hopefully those are much, much lower levels than the common majors. So overall, a very good method that's been around for a while. ICP mass spec users have been using this method for a long time. And then standards, of course, for this method have been developed for a while as well. And usually what you'll have when you want to run EPA method 200.8 and you're looking for a good stock standard, you're going to have most of the elements available to you split out across a few different stock standards. So the majority of the trace elements that you're looking for in this method are going to be available in dilute nitric, which is great because a lot of mass spec users want to stay away from HCl because of potential interferences. The internal standards are also available in dilute nitric. The only one that stands out is mercury, and I'm going to touch on some of the issues with mercury here in a moment. But mercury is usually available in either dilute nitric or dilute HCl, and usually it's separated out from the other analytes. And I'm going to touch on the reason for that here in a moment, but it's just something to keep in mind as if you're running this method. These are what's available. And for most of the time, this is actually a really nice method because almost all of the analytes are going to play nicely with each other. They're going to be compatible and stable and dilute nitric. So you don't have to worry about, increasing HF concentrations if that's going to drop something out of your solution. These all play relatively nice, and you're not going to have that issue. So now that we've got our list of analytes, you really have to focus in on selecting a good mass for each of those analytes. And how do you do that? The first recommendation I would make specifically for this method is you have to decide if you're going to include your major elements in your standards or not. There's pros and cons to each, but if you do, you want to make sure that you are looking at the interferences that are going to be present from those major elements. So, for example, if you add iron at high concentrations compared to the trace elements, expect to see larger interferences on elements like chromium and nickel. And when you're adding some of these majors at much higher concentrations than the trace elements, sometimes you are going to have to worry about the oxide formation rates that you normally wouldn't have to worry about if all the concentrations were on the same level. Something like potassium oxide can have a big interference on manganese if the potassium is a much higher concentration than the manganese. Same with calcium oxide on nickel. Those are all things that you're going to have to worry about. You also have to keep track of the interstandard interferences, and these are going to be present, because you have all these elements in your standard. So elements like zinc and nickel, indium and cadmium, and antimony and barium are going to have some natural interferences that will appear on each other. They should all be at relatively the same concentration level in your calibration standards. But also keep in mind that if your sample does not have all of the elements present, you may have some interferences present in your calibration standard that are not present in your samples. And usually that leads to a low result, a false low bias in the data. And that's usually what happens when we have tech support cases where people are reporting low results. It's usually because there's an interference present in their calibration set that's not present in their sample. So just diving a little bit deeper on selecting a good mass. I always use Excel to sort of go through this if we're doing a new method development. You can do it for EPA method 200.8 as well, but EPA method 200.8 has been out for a while. People know the good masses. So this is how I would go through it sort of step by step. Once you have your list of elements and you roughly know what your interferences are going to be, you start mapping out all of the potential isotopes you can use and then map out the potential isobaric, oxide, doubly charged, and any other polyatomics that might come from argon or chloride. And if you're worrying about chloride, make sure you look at the polyatomics that could happen from mass 35 and 37. It's pretty common that folks will not think about the chloride polyatomics that come from chloride 37. So just keep that in mind as well. Like I said, I use Excel to do this. What you see on the slide here is kind of a pet project that I've been working on and hope to soon have this released to our customers and whoever as part of our technical resources on our website. Once it's in a little bit more easy to use format, this just goes through and tracks all of the isotopes, their isotopic abundance, and then gives you a column where you can plug in concentrations. So if you're trying to design a calibration standard, but you expect that you're going to have majors present in the matrix, for one reason or another, you can alter those concentrations and then get a real-time view of the potential interferences and the percent max potential interference you would expect to see by entering in your oxide and doubly charged interference rates that you should see on your ICP mass spec performance reports. So usually those are 2%, 3%, something like that. But you can plug all that stuff in, then you get a sort of a good idea of, okay, what are going to be the major interferences present, and it helps you select a good mass or not. So Excel is definitely a useful tool to keep everything straight because trust me, I've tried to do this on paper before. If you're looking at a lot of elements and get really tricky really quickly, and it's much easier to organize in something like Excel. So I promised we would circle back to mercury. Especially with EPA method 200.8, there is a reason why it's usually split out from stock standards. And there are a couple issues with mercury. So the first one I'd be remiss if I didn't point out is that mercury and lead, both trace elements in this method, have an isobaric interference. The good news for that is you can easily choose other masses for lead and mercury if that's a concern. because there are a lot of good masses for both of those elements. So I mentioned before that mercury would be available in either dilute HCl or dilute nitric. The reason for that is chemical compatibility. So let's start off talking about when mercury is present in dilute HCl. You're going to have increased stability, but the issue is if you try to mix that mercury stock that's in dilute HCl and down to a working concentration with the other elements that are in nitric, that HCl carryover is going to cause silver to precipitate and drop out. You can get around that by increasing the HCl concentration to about 10%, but most folks don't want to do that, and I wouldn't recommend that for ICP mass spec. That concentration is a little bit too high for what I would recommend as the matrix for ICP mass spec runs, and you're just going to have more corrosion problems to deal with your instrument, so I would recommend against that. Most folks, when they buy mercury for EPA 200.8 and HCl matrix, what they do is they split that out and they just run mercury as a separate calibration curve in dilute HCl. So the other option is you can buy mercury, your stock in dilute nitric, but there are a couple of concerns. First off, because you're looking at mercury at really low concentration levels, you want your stock standard to not be at a super high concentration, or you're going to have to do a bunch of dilutions down. The only issue with that is mercury at concentrations of 100 ppm or less should be stored in glass if you're keeping it in HCl. The reason for that is you see mercury absorption onto plastic bottles. So if you're storing it in glass, you're not going to see that absorption. It should be stable for longer. But the issue with that is glass bottles, at least all the ones that we've tested, have contamination. And particularly for this method, we've always found aluminum, barium, nickel, and zinc present in glass bottles. So that's a major issue. You can stabilize the mercury with 1 ppm gold to keep it in dilute nitric in a plastic bottle, but your stability is going to be very limited, especially when you're at working concentrations for this method of about a ppb or lower. I would expect stability to be limited, even stabilizing with gold, to a week, maybe a little longer, maybe a little less, somewhere around that time period. But you're going to have to constantly remake these working solutions to keep nitric in dilute nitric acid with the mercury with all of your other elements. So it can be kind of a headache to go through and remake all of those working solutions. EPA method 200.8 and section 7.4, where it talks about making calibration standards, it specifically points out that you could split out barium and silver. Now, this method was written a long time ago. I'm not exactly sure why they pointed out specifically barium and silver could be split out. Those are perfectly compatible and stable with most of the other trace elements. Again, with the exception of being mercury and HCl. Those are going to be fine. I would recommend, instead of splitting out barium and silver, take a look at splitting out zinc and cadmium instead. So if you split out zinc and cadmium, you're going to avoid some of those inter-standard interferences. So remember, those are the interferences that would be present in your calibration set that may not be present in your samples. So that could prevent you from getting some low bias data. The only issue with this approach is it would require you to run 2 sets of working standards. So if you're wanting everything in one calibration set only, you're going to want to keep everything together. But if you're already splitting out mercury and HCl and you're running an alternate calibration set anyway, you can add zinc and cadmium to dilute HCl and it's going to be fine. So if you're running an alternate set of calibration standards anyway for mercury, you can pull zinc and cadmium out of your main set, throw it into your mercury set, and it's going to be an even better method with less potential interferences within the standard set. The good news about that approach as well is if you do decide, again, that you want to throw the major elements into your calibration standards, those major elements are going to be stable in both dilute nitric and dilute HCl. So you can matrix match your standards to your samples with those major elements in both of those calibration sets. So I've talked a lot about interferences within the standards. I did want to briefly touch on what happens with the interferences within the sample, because again, you can't control your samples, but you can control your standards. From ICP mass spec, that's where constructing interference correction equations come in. And for 95% of users out there, they're going to rely on the instrument software to apply these correction equations. And that's definitely the easier route. If you are kind of curious as to what those correction equations are doing, it's just doing a little bit of math once it knows the interfering element and you need to know some of the nature of the interferences. So is it an isobaric interference? Is it a polyatomic that you're worried about? Isobaric interferences are relatively easy to correct for. It's using a ratio of the isotopic abundances and the ratio of some signal that's present on a non-interfering mass. So relatively straightforward. Polyatomic requires a little bit more work. You have to characterize the oxide formation rate or the polyatomic interference rate. It's going to be a little bit more work to do. If you are interested in that, I would definitely recommend you check out Ivy Ignite. So it's our virtual training academy, and we have a whole course on Ivy Ignite about how to construct these interference correction equations. So we take you through step by step and how to set them up, give you Excel files to download and work through so you can go step by step and get a little bit better idea of what your instrument software is doing in the background. So if you're interested in that, definitely check out Ivy Ignite. And speaking of Ivy Ignite, this takes us to close to our last slide. You can scan that QR code and that'll take you to a free trial of Ivy Ignite. We have a couple free courses on there. That is our official virtual training academy of Inorganic Ventures. A lot of good training videos on there. And again, free courses available through Ivy Ignite. We also have a ton of resources on our website. So if you have not checked out the inorganicventures.com website, definitely check it out. Like I mentioned before, you'll see previous webinars on there. We have a great interactive periodic table. We have lots and lots of ICP operations guides, trace element guides, sample preparation guides. There's just a ton of stuff on there. And then we also put out new resources every week, at least in the form of a podcast. New episodes of our Bench Boost podcast come out every Tuesday, where myself and a group of 3 other chemists sort of sit around and we talk over topics each and every week. So feel free to listen into that. Again, all those resources available for free. Just check it out. And lastly, I will mention that if you are in the Houston area this December, we are coming to town December 10th and 11th for a 2-day ICP workshop. And actually, Sergei is going to join us this year as one of our guest presenters. So it's going to be a great time. And if you want to learn more about that, please visit the inorganicventures.com website. There's more information there, or reach out to myself or info@inorganicventures.com. We'll send you all the information, but it's going to be a great event. And if you can make it, I hope to see you there. All right, so I'm going to go ahead and stop sharing my screen, and we're going to go into the questions here.
Sure.
All right. So give me just a moment here to pull up the question list. All right. So the first question up was, do these different nebulizers have the spray chamber built in, or do these nebulizers also need to be connected to a spray chamber and then the torch?
Yeah, nebulizing and spray, it's a good question, is the part of the sample reduction system. And I was focusing just on the nebulizers to save time. But yeah, the nebulizers are not built in as one piece. So they have to be used, of course, with the spray chamber, which functionality of it to remove filter the larger droplets. And then obviously it will be connected to the torch. On I think one of the slides, there is a combination of the what we call impact plate nebulizer or optimist vortex with the spray chamber, because due to the certain orientation of the nebulizer, it requires its own spray chamber.
Perfect. All right. Next question, Sergey, is about cleaning their nebulizer. So how would you recommend a cleaning process?
Yeah, there are a bunch of resources and with nebulizer manufacturers and our recommendation and ICP manufacturers, but the basic idea is, and you can go with expensive Teflon type of syringes that being offered, but we recommend a simple thing. You can get a lab syringe that every lab has connected with a tube. We have a video on our website, and you can front flush it, back flush it, nebulizer, or you don't have to go through like this extensive procedure of back flushing or front flushing. You can just simply soak it in nitric acid, or 5 to 7% nitric acid, or soak it in the lab detergent. And just get a high concentration, about 20-25%, something like Citranox or Fluke RBS concentrate, and that actually does the trick. So I recently was able to actually clean up the nebulizer that had built into the glass just with using that and a little bit of a heating. So I heated the solution in the microwave and then it left it overnight, and then it did the trick.
Awesome. All right. Sergey, which nebulizer would you recommend to analyze crude vegetable oils?
Yeah, that's been touched in the presentation, and crude oil, like the publication that I showed, the example of phosphorus, that was in crude oil, and but any type of oils, as I mentioned, yeah, they should be run with any non-concentric nebulizers. So I would not recommend to use concentric because you're going to be running into trouble with either with clogging it or with extensive cleaning. So any non-concentric nebulizers will do the job.
Perfect. Next one is how much does the Optimus nebulizer increase the detection limits on ICP OES using the impact plate?
Yeah, the Optimus Vortex with the impact plate. So on average, we see about factor of 2 improvement in efficiency and detection limit. Again, depends on the element and how you tune it, but this is what the ballpark is, about twice or double the sensitivity and improvement in the detection limits.
Right. Next one up is how much effect does the spray chamber choice have on the nebulizer's ability to perform?
Yeah, the nebulizers will, it's independent thing. So the nebulizers will perform regardless of the spray chamber, but they do work in concert, in combination. And the main two types are spray chambers with internal baffle or without baffle. So the difference will be if you use these, and again, it depends on the choice and the preference sometimes, but the technical ability is that the spray chamber without baffle will get more sample into the plasma, and usually you would see that will result about 20% higher count, so high signal, and some people love it, right? But with that, the filtration action or feature is not going to be as efficient in terms of the filtering the large particle. That what the spray chamber is used for. So you may have a higher RSD or higher noise. So then, if you use the baffle spray chamber, the signal is going to be slightly less, but the precision is going to be better. So the detection limits is probably going to be about the same. Also, the non-baffle spray chamber has a smaller surface. You may get a little bit better in-out time. So yeah, that becomes a question of the preference. Now, for organics, I think the ICP manufacturers and we do recommend using the baffle spray chamber because of the efficiency and volatility and all of these effects.
Got you. All right. Next question is argon humidification necessary when the total dissolved solids is, say, about 5%?
Yeah, that's a very good question. Yeah, that's again, I did not touch the argon humidification here, but absolutely. Even with less amount of TDS, even when you get to maybe even 3 or 1%, so then the argon humidifier we advise to use if you run a lot of samples. When you have even 5% TDS, but you ran a couple of samples, your customer, your client sent it to you, said, well, take a look at this. I don't think it's worth going in the investment for the argon humidifier. You can run just a couple of samples without any humidification, even with 5% TDS, quickly with the right nebulizer. But if you run even 1%, but you run hundreds and hundreds of samples to get you consistent performance, so you don't have to worry about salting up of your nebulizer, then yes, the argon humidifier is certainly a must to use.
Right. All right. Sergey, this next question says, we currently use a Bergner Teflon Miramis nebulizer for our ICP OES. How often would you recommend changing the tubing attached to the nebulizer? and it mentions that cleaning is minimal for this nebulizer. What would you personally recommend for maintenance to avoid interior clogs and contamination?
Yeah. So this was a question from Adam, one of our customers. Yeah. I would, our approach is, or my approach is, don't fix something that works, right? So the enhanced pedal pulse or Burger Mirror Mist is a pretty solid nebulizer. So that's been used for in your application because of the HF resistance. And yeah, the manufacturer doesn't recommend too much of a cleaning. Shouldn't be required too much of a cleaning. So if you don't see anything that concern in terms of the performance, I would not change the sample adapter. You would have something ready to go, but unless you get like your samples are not completely digested and you get some a particle coming into the sample line and you see a restriction there and you would not be able to clean it, then that would be a time to change it. Otherwise, I think it should be fine.
Awesome. Thank you. All right. Next one is, how can we determine the stability of our nebulizer?
Yeah, that's a interesting question. So the key idea and challenge here is to separate the stability of your instrument from the stability of your nebulizer. And I think the way to possibly do it is like if you need to have a nebulizer that works well, right? That's kind of your reference thing. And the manufacturer sometimes include in their package the what's called default nebulizer or whatever. So whatever the reference nebulizer is, works. So you get this and you see the stability and they make sure the instrument is performing well, right? Instrument is stable. Then you can run something. It doesn't have to be anything difficult, but run something like simple solution with manganese or any common elements. Just monitor a few elements and maybe argon lines and run it for a few hours every 10 minutes on the auto sampler, and then you will see the stability and they can make some kind of a judgment, and then you can compare it to the same performance for the reference nebulizer. So that would be one way of doing it.
Great. And I think you kind of answered part of the next questions about what parameters can we check to ensure the nebulizer is working properly. But this other person had a question about they're currently using a PFA microflow nebulizer. Is there a better option or a more robust nebulizer than this one?
Yeah, that's the parameters is one of the things that I mentioned pretty quickly in the presentation. So when you need to determine the health of your nebulizer, so one of the parameters to look at, main thing, is the nebulizer pressure or back pressure, as we call. Many ICP manufacturers now in their softwares, or some of them even warn you if it goes over a certain level, it gives you, oh, your pressure is up, just monitor it. But I think every ICP manufacturer software at least have it that you can look at it and display it. So that would be the one thing to do. If the pressure is elevated, and you should have a record of it. For example, you apply 1 liter per minute of the nebulizer flow, and you say, okay, my nebulizer has whatever 150 kilopascals, or 2 bars, or 30 psi, depends on the area of the rod that you're working with. And then, so you have this as somewhere recorded. And then if you see the pressure goes higher, then there is a restriction, and then you realize you have to take a look and maintain it and do whatever to bring it back. And if the back pressure is lower, so then you have a leak somewhere in the sample reduction system. So the other simple thing that you can do, and I showed it in details in one of our first webinars that we did back last year, actually, for troubleshoot. It was devoted to troubleshooting. There is a recording available on Inorganic Ventures website or on Tube on our channel, or we can send it to you. But I showed there that you can simply look at the mist. and you put some on the background, which is a piece of a black paper or something like with a dark background, and then you look at the mist, and just by looking at the mist, you will be able to tell if your nebulizer is working well, if it has a trouble, because the mist should be straight. It should not go to any direction. It should be quite, solid, intense. And then with a little practice, you will be able to make a valuable judgment on that. In terms of the PFAST nebulizer, yeah, this nebulizer is good in terms of their efficiency. It's good for semiconductor industry, the HF resistant. That's how it was brought up. But I see it's now being kind of pushed to different areas where it doesn't belong. I'm sorry. And that's why people are having trouble with that, because this nebulizer, again, according to the manufacturer, cannot even backflush. And I don't know what particular application the owner of the question is, or the author of the question does, but yeah, there are definitely number of nebulizers on the market that more robust. If that has to be HF resistant, there is enhanced parallel path nebulizers that I mentioned in the presentation. There is the nebulizers we offer that made by Cyberlex that actually backflushable and has very similar design and performance than PFAST. And there is way more choices to get more robustness than PFAST.
Awesome. All right. Next question up here. And this is, I think, again, sort of touching on nebulizer cleaning. How would you recommend that we remove buildup, or what would be the recommended way of cleaning a nebulizer?
Yeah, that's already a kind of, I think, answer. So you can refer to my previous answer. So the nebulizer manufacturers don't recommend any, sticking wires or ultrasonic. So that's no, right? But the removing the blockages, right? So again, backflushing either with the lab syringe, and we have a video on our website, and I can share with the author of the question offline. So then, again, depends on what get there. If there is a salt up, so you could try to soak it in nitric acid, 5 to 10%, and maybe heat it up a little bit, leave it overnight. If there is a metal that will coming from the corrosion of the parts that connected to the nebulizer, that should dissolve quite often. And this is even the Teflon nebulizer struggle from that. When you're running solution with high sodium content, especially, the sodium presence gets and built up the salt up that getting stuck, believe it or not, even to Teflon, that's actually very hydrophobic. So in this case, when normal cleaning doesn't work, and again, you can try, surprisingly, the soaking in lab detergent with a high concentration with a bit of a preheating before actually worked. But if it doesn't, so then what we do for our nebulizers, we offer cleaning. And in this case, we don't recommend it for our customers, especially the one that don't deal with HF. But a glass or quartz nebulizer can be even the Teflon can dip briefly into 10% HF, and that will shaken up the stuck deposit to the surface and will clear it up. But that's a pretty extreme case. Normally, again, back flushing with any of the device that's available, whether it's a lab syringe or more expensive accessory, and soaking in nitric acid or lab detergent. Or if you run organics and you have something, a residue from there, you can soak it even in acetone.
Awesome. All right. And then the last question. Our axial lens has been picking up film-like deposits, and we are replacing them more often recently. We are seeing lower sensitivity in the axial view. Could this have something to do with the nebulizer we are using?
Yeah, that's unlikely with the nebulizer. So depends on what the instrument is, what design is of the axial instrument, because there are different configuration of the axial view. I don't know what it is, but what particular is, but there are some axial views with optical plasma interface. There are something with cross-jet when there is a flow that run across the plasma, and there is a counterflow of extended torch. But in any of these cases, the deposition or degradation of the lens on the axial, it's unlikely related to the nebulizer. It's more of a sample types, and that could be run, or something related to the particular design, or maybe not enough flows to get there. But all the instruments struggle with it with the time, and it could be part of the regular maintenance.
Yeah. Okay.
On the instrument, not on the nebulizer.
Awesome. Well, thank you so much, Sergey. Just a reminder, there were about 10 plus other questions that that Sergey has been kind enough to answer in writing. So you will get those as well, probably with the invite to view this recording. But if you are viewing this later and you want to get those questions, please feel free to reach out to us so we can get those to you as well. Do want to say thank you so much for your time. And until next time, I hope you have a great rest of your day. And Sergey, thank you so much for spending your time with us and giving these great presentations and great answers.
Thank you. Thank you for inviting me, guys. It was always fun and a pleasure. Thank you.
Thanks.